let's define magnetic flux. Magnetic flux is this symbol that we are going to know and love. We're going to make our flux lines in this nice blue. And this is our symbol for magnetic flux. And the unit for magnetic flux is the Weber, or the Weber, if we want to butcher it to that, or the Weber, if some people like to say that pronunciation in that way. But I'm going to say the Weber. So WB is the abbreviation for a Weber. The magnetic lines of flux that I'm talking about, we can look at from a bar magnet perspective or from a current carrying conductor perspective. But if I just look at a bar magnet, which is, a thing that's sitting on my desk, it's a piece of ferromagnetic material that has the ability to induce, magnetism is induced in it. So my lines of flux are those lines that I can actually see if I put some magnet filings on my desk. I can actually see that they align themselves in lines, in separate lines, and those lines go out of the North Pole and they go into the South Pole. So these magnetic flux lines, these are the flux lines I'm talking about. They have a direction always out of north and into south, always on they are always continuous through the material. And as they continue through the material, they happen to be going from south to north. They always concentrated at the poles, and they are always trying to avoid each other when they're up here in free space and don't have ferromagnetic material to go into. So they tend to repel each other. But these are the magnetic lines of flux that I'm talking about. These are also, we've talked about these as magnetic force lines. So I'm going to call them magnetic flux. I'm going to call them flux lines. I'm going to call them lines of force. I'm going to call them magnetic force lines. It's actually called magnetic flux. The magnetic flux are those groups of lines that go from the north to the south pole. If they are really, really, really close together, then they are strong magnetic force. If they are spaced far apart, if these flux lines are spaced far apart, then it is not a strong magnetic field. And we have all experienced a strong magnetic field and not a strong magnetic field, even just in our regular life. You buy cheap magnets, they're going to be those magnetic flux lines. There's fewer of them, and they are spaced farther apart. So this is weak. This is just a weak magnetic field, and this is a strong magnetic field. And in one situation, you might have weak and strong. In this situation, they are concentrated near the poles because they always want to get into a ferromagnetic material. And they will even not join together. They won't touch, but they'll even come closer to each other if there's a ferromagnetic material to get into. So they're more dense there. So that's stronger magnetism near the poles. Whereas over here, there's a bit of magnetism, but not a lot. So over here it's weak magnetism, and over here it's strong, it's concentrated. So this is going to change. How strong it is going to change depending on the material of this magnet, right? If this is a really magnetic material, it's going to be stronger. It's going to have more lines of flux. We can actually count more. The geometry matters, because if I change this to a different shape, like I spin it around like into a circle called the toroid, then I can do all sorts of things with these magnetic lines of force. And of course, the distance matters as well, because these ones way out here are weak, whereas these ones in here are strong. And a distance from the magnet, if you think about like an induction range actually works with magnetism, with magnetic lines of flux, and Faraday's law. So the further you get away from that situation of these magnetic flux lines, the less magnetism there is. So if you're standing a foot away from that inductive range, you know that those flux lines don't want to be out there. They want to be closer to the ferromagnetic material. It's going to be very, very, very weak out there. All right, so they do have properties similar to the current. in an electric circuit to current measured in amps in an electric circuit. And we can kind of think about that if we go back to the definition of an amp. And if we say, oh, well, I put more current through these current carrying conductors, I'm going to get more magnetic attraction. If I put less, I'm going to get less, because we know that current is directly related to the force, and the force comes from the magnetic flux lines. So then current, as current goes up, more electrons flowing over time as the rate of current changes, which is our amps, then we're going to get more force, which implies that we have more magnetism. So it is similar to current because it's related to current. The unit is a Weber, but a Weber is a count. This is actually a count. So a Weber is equal to magnetic flux. It is equal to 10 to the 8, or you can say it's equal to 1 times 10 to the 8. 1 times 10 to the 8. If you like to do your math that way, which I do, magnetic flux lines. That's all a Weber is. It's actually a count of magnetic flux lines. And we're going to call 1 times 10 to the 8 of these a 1. 1 Weber. Now, how many do I have up here? Let me see. I'm going to do a count. 1 times 10 to the 8. This is a number. This is a count. Let me count what I have in my diagram. I have 1. I have 2. I have 3. I have 4. I have 5. I have 6. I have literally 6 lines of flux. Do I have 6 Webers? No. This is nowhere near 1 Weber. That is much, much less than 10 to the 8, which is 1 Weber. So let's talk about what a count is. So a count, we have other counts. We have 1 dozen. And that's a count. You count your eggs and you count 1, 2, 3, 4, 5, 6. We count up to 12 and we call that a dozen. So that's a count. We count a baker's dozen. Baker's dozen. And when we count a baker's dozen, we count 1, 2, 3, 4, 5. We count up to 13, and we call that a baker's dozen. We like, it's a popular count, so we put a name to it. Avogadro's number. I don't remember what it is. But it's a number. A mole, 6.022 times 10 to the negative 23. Mole, if anyone's in chemistry, is, I think, 6.22 times 10 to the 23, I think.
Yes, that's what it is.
All right, thank you.
Sounds very familiar.
It is a count. It means, like, we have to count a lot of those. That's a big number, right? Dozen, I mean, couple. Couple in the English language, a little bit slang for a count of 2. 1, 2. I have 3 couples. I have 3 couples of flux lines over here. I have nowhere near 10 to the 8 though. So what Weber said, said is, I'm Mr. Weber, and I get to decide my units. I think there's magnetic flux lines, because this is actually all still theoretical, but I think there's actual lines because I see them when I put metal filings near a magnet. And I want to work with some math, so I need to kind of standardize the group of lines that I'm talking about. And I want to standardize those groups of lines by calling a count of them. He could have said, I'm going to count 12 of them and call that a Weber. If he counted 12 of them and called that a Weber, we would say magnetic flux equals 12 equals 1 Weber. It's just a count, right? But Mr. Weber did not say that. He said, I'm going to count out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, all the way to 1 times 10 to the 8, which is a very large number. And if we count out this quantity, I shouldn't say count, I should say it's quantity, then we get to give it a special name called a Weber. All right. So lots of numbers like that is just a count, but it's really, really big. It's a really, really big number. It's a little bit too big for us to use. It's kind of like Pascal, right? Pascal's number is a really big number. So or a really small number. So we usually use megapascals. And I'm just saying we usually use microweber, because it's just so big that we usually don't have a Weber. We usually use microweber. If we put everything in Webers, it can be correct. We can be, yes, correct, but a little bit weird. So we should be prepared to use microweber. And 1 microweber, of course, I would just move over the decimal place, right? And that would be to get to micro, knowing our our SI unit notations would get us 100 lines of flux. So that's a Weber. And we can use that Weber for lots of interesting calculations about magnetic induction, etc. And that's the Weber.